Good morning, everyone. As we have started with the last chapter, magnetic effects of electric current, we will be moving ahead with the remaining part. So, in your textbook, this is again an activity. What is done in this activity is you can see the electric circuits being set up, battery, key, closed key, and then there is a wire, and then there is a compass needle kept. Can you compare the two figures, figure 13.5a and 13.5b, and tell me the difference? You can go through the caption that is there, and then you can frame your conclusion. What is the difference between figure 13.5a and b? Spot the difference. Yes, reverse electric current. So due to reverse electric current, what is happening? Yes, direction of current is reversed, due to which what is happening? If you see figure 13.A, the current is flowing like from positive to negative, and over here the conductor is there, so the current is going like this in the downward direction. Okay, arrow is like this. So when we keep a compass needle nearby to that conductor, we can see the deflection in the east direction. You can follow these conventions. Okay, so you can see the needle being deflected in the east direction. Now, if you see figure 13.5b, again the current is flowing from positive to negative. Okay, the flow remains the same, but now the current is flowing in the upward direction, as you can see this arrow. Now, what you will see, the deflection is in the opposite direction. Earlier it was in east, now it is in the west. So, what does this signifies? What does this signifies? This signifies that we can change the deflection of the magnetic needle by changing the direction of the current. Okay, we have seen that current and magnetism are both interconnected things, are both interconnected terms. So if we want to reverse the direction or deflection of the magnetic needle or magnetic compass, then we have to reverse the direction of the current. This is what is a simple thing that they want to tell you in figure 13.5. Now we will move to figure 13.2.1, magnetic field due to a current through a straight conductor. What does this mean? This means that we are going to study about the magnetic field around a conductor which is a straight one. Okay, now in this case the conductor is straight one like this. We will see what kind of magnetic field is formed, what is its shape, and things like that. Okay, so I will read activity 13.5. Take a battery 12 volt, a variable resistance, an ammeter of this much range, a plug key, and a long straight thick copper wire. As we have seen, we are going to deal with straight conductor. Okay. Insert the thick wire through the center, normal to the plane of the rectangular cardboard. Take care that the cardboard is fixed and does not slide up or down. So you can correlate this instruction number 2 with the figure that is there, this one. Okay, there is a key, then there is a battery, ammeter is always connected in series, so you can just cross check that also. There is variable resistance, then there is a conductor. You can see this conductor is a straight one. Okay, and we have pierced it through the center of the cardboard. So suppose if this cardboard is A, B, C, D. Connect the copper wire vertically between the point X and Y as shown in figure 13.6a in series with the battery, a plug, and the key. So you have to make the connections. Now what you are going to do, you will be sprinkling some iron filings uniformly on the cardboard. You may use a salt sprinkler for this purpose, so as to maintain the uniformity. Now once you will make the key closed, the current will start flowing from positive to negative. What can you comment about the pattern of these iron filings? What can you see in this figure, figure A? How are they arranged? Now when current is flowing, obviously magnetic effect will be generated. This we have been learning right from lecture number 1 for this chapter, that whenever a current flows through a wire, it generates a magnetic field, it generates a magnetic effect. So in this case also, current is flowing through a straight copper wire, it will generate magnetic field. So what can you comment about the pattern, how the pattern looks like for magnetic field? It is circular, just circular. What do you use for the circles which have a common center? It is a concentric circle. So the first MCQ that could be asked is about the pattern that you observe when the current is flowing through the straight conductor. So there you are given four options: concentric circle, then some other shape, something like that is given. So you have to remember that whenever it flows through a straight conductor, the pattern which is formed is like this. Okay, so let us study the properties. We will see why it is concentric ahead. You can also see in this figure how it is in concentric manner like this. Okay, now if I increase the current, will the magnetic effect or will the magnetic field increase in that case? If I increase the current, in that case, will the magnetic effect be also increased? If you see, they have kept a compass over here, P. It is a compass. They have kept it nearby to this conductor, which is generating a magnetic field. So will that be possible? Yes. Why? Because we have seen that whenever a current flows through a straight conductor, it generates magnetic field around itself, and now you are increasing the current, so obviously the magnetic field generated will also be high. Yes or no? We have seen it, right? Whenever a current flows through a conductor, it generates magnetic field around itself. So B is the symbol that we used for magnetic field. Then I is a symbol that we use for current. So this we already know. Now what is the relationship between B and I? So B is directly proportional to I. Okay, if you increase the current, magnetic field strength will also increase. If you decrease the current, the field strength will also decrease. Okay, now the second thing, if I place a compass needle over here, suppose, there will be some deflections. That is for sure because magnetic field is generated. Now, after keeping it over to this point, now I will shift it to this point. In which of the locations you will find the deflection more? Whether when the when compass is placed close to the wire or when it is away from the wire. In which case you can feel the deflections to be more close to the wire. Why? Why so? Yes. Yes, because electric current is flowing and there the field is much and more stronger. Okay, the magnetic field is much and more stronger over this point than to the point when you will go ahead. I mean, move far away from that. So the second relationship that I can derive is B is inversely proportional to 1 over R, where R is the distance. Can I say that? As you increase the distance, the field strength will be decreasing. As you decrease the distance, the field strength will be increasing. Inverse relation. Okay, so remember these relations. This is one thing. We find that the deflection in the needle also changes. In fact, if the current is increased, the deflection also increases. It indicates that the magnitude of the magnetic field produced at a given point increases as the current through the wire increases. So this gives the relation B is directly proportional to I. Then second, the magnetic field produced by a given current in the conductor decreases as the distance from it increases. So as you will move far away from that conductor, the deflections will be less because magnetic field will decrease. Okay, so the relationship that you can establish from this point is B is inversely proportional to 1 over R. From figure 13.6, it can be noticed that the concentric circles representing the magnetic field around a current carrying straight wire becomes larger and larger as we move away from it. So any doubt in this particular section? How the current flows through a straight conductor, what kind of pattern you observe, what kind of relationships you can deduct from that. Okay. Now now we will see why do we get those. This is a rule that we have to use for finding the direction of magnetic field. So we know that magnetic field is a vector quantity. It has there is, but it is not there for 10th. You can just remember the relation. B is directly proportional to I and B is inversely proportional to 1 over R. Okay. Right hand thumb rule is basically a rule which helps us to know, or which helps us in finding the direction of magnetic field. In the first lecture, we have seen that magnetic field is a vector quantity. It has vector quantity means what? It magnitude is also associated and direction is also associated. Magnitude we can find with some formula. Okay, we can find it using some formula. But what about direction? So for finding the direction of magnetic field associated with a current carrying wire or current carrying conductor, for this we will be using this rule, right hand thumb rule. This rule is also called as, just wait, you can get the name from here. Corkscrew rule, this Maxwell corkscrew rule. Okay, so from any name it could be asked, right hand thumb rule or Maxwell corkscrew rule. Right? Now what does this rule says? This rule says that imagine that you are holding a current carrying straight conductor in your right hand such that the thumb points towards the direction of the current. Suppose this is a conductor, right? Now the current is flowing in the downward direction as the arrow signifies. So what you have to assume? You have to assume that you are holding that current carrying conductor with your right hand, because this is a right hand rule, right hand thumb rule. Now the thumb should point to the direction of the current. So if the direction of the current is in the downward direction now, so your thumb should also point in the downward direction. So in this case, I can say that the thumb is signifying the direction of current. Okay, where should your thumb point? Your thumb should point towards the direction of the current. Now, depending upon how your other fingers, four fingers, middle finger and all that curl around the wire, that will give you the direction of magnetic field. We will see how, but just for information, the statement is very, very important because this will be going to be a subjective exam for term 2. So the chapter is for term 2, so you have to go through the statement of this particular rule. Okay, the statement is important. I will just show you one video.
In this video, we're going to see how to remember the direction of the magnetic field. So let's say this pen represents our straight wire carrying an electric current. And let's say the current is running this way.
Now see, we are dealing with a straight conductor. So in the exam, a real conductor won't be provided. You can assume your pen to be a conductor. Okay.
Then we know the magnetic field around it will be in circles. But that can be in two directions. If I use a bangle to represent the magnetic field, then it can either be this way, where on the top the magnetic field is to the right, as you mark, or it can be this way, where on the top the magnetic field is towards the left. So how do we remember what direction is going to be the question? So a simple rule that we're going to use over here is called the right hand thumb rule. It says that you take your wire and you clasp it with your right hand, not the left hand, right hand, such that the thumb represents the direction of the electric current. So over here, notice the electric current is this way. So my thumb has to point in that direction.
Because now he has considered that the current is flowing in the upward direction, therefore his thumb is also pointing in the upward direction.
Then the four encircling fingers will tell us the direction of the magnetic field. So over here, notice the encircling fingers are telling me that the magnetic field on the top is to the right. So now I know that the magnetic field has to be this way.
It will be in this direction because if you have seen how the remaining fingers were curling, it was in the right direction. Yes or no? Did you see how the remaining four fingers were curling? It was in that direction, right direction.
Field has to be this way. Then on the top is to the right. And if the electric current were to reverse, let's say downwards.
Now in this case, we have assumed that the current is flowing downward, therefore the pen is made downward. Now where will your thumb go? Where will your thumb go now? You can perform it simultaneously. Okay, downward, yes.
Electric current was downward. Now I would clasp the same conductor with my right hand this way. Because the thumb should point in the direction of the current, this way. And so now look at the four fingers. The four fingers are telling me that the magnetic field on the top is to the left. You see that? It's to the left. Therefore now the magnetic field is going to be this way. Sometimes you have to figure out the direction of the magnetic field at a specific point around the conductor. For example, again, let's say we have a current carrying wire, which is carrying current in this direction. And I ask you, what is the direction of the magnetic field at a specific point over here, to the right of the conductor? How do we calculate it? Well, yeah, the first step is the same. You use your right hand clasp rule and figure out the direction of the magnetic field line. It's going to be this way, to the right on the top. And angle again. This. And once you have the magnetic field, to figure out the magnetic field at a specific point, you just draw a tangent to the field. So I want to find out what is the magnetic field at this point, to the right side. Alright, so I want to know what is the magnetic field at this point over here. So you have to imagine a tangent to this circle at this point. What would that look like? Well, I'm just going to tilt a little bit so that you can see it properly. If you draw a tangent over here, notice you can draw two tangents, one this way, one this way.
So now we want to find the magnetic field at this point, right? So the tangents could be drawn this way and this the other side way. So we will consider the front way. Why? Because this is how your current, this is how your magnetic field is flowing.
But since we already know the magnetic field is going to run like this, the tangent has to be down. So the magnetic field to the right of the conductor is going to be downward.
Okay, so now in this case, the magnetic field will be downward.
Here I could have just rotated this angle also. Notice when I come to this point, hopefully you can see arrow mark point.
See, you can see the arrow going downward.
So what do you think would be the magnetic field direction at the bottom? You try and do this yourself now?
Yes, you can try it. At the bottom, what will be the direction of the magnetic field? Just perform it and let me know. At the bottom. No, it is not straight. It is going down now.
Pause the video.
See.
So what do you think would be the magnetic angle also?
See how the arrow is moving. At this point, it is going down.
You can see arrow mark points down.
Okay, नीचे की तरफ
So
जा रहा है.
what do you think would be the magnetic field direction at the bottom? Try and do this yourself now. Think about this. Pause the video and think about this. At the bottom, over here, at the bottom. Well, again, I'm finding this a little hard to hold. Again, I'm going to hold it this way. So if you come right at the bottom, again, imagine drawing a tangent over here. What would the tangent look like? Well, a little bit so you can see. The tangent might be this way or this way. But again, since I know the magnetic field runs like this, the tangent has to be in this way.
That is why he has considered this way tangent on and not this way, because your current is flowing in the downward direction.
I'm going to create that.
Not current, sorry, field.
Arrow mark, the bottom. With this direction. Now, doing it this way, it's fine if you have a prop with you, like if you have a bangle and you have an arrow mark attached to it. But what if you don't have access to it? Imagine
Now, if you don't have a bangle, you won't be having a bangle in exam, but still you can perform this. Just see.
At least it used to be difficult. So I'll tell you what I used to do when I didn't have any groups. So again, first step, clasp with the right hand, same steps. Now, I imagine the magnetic field running like this. So you also try and imagine this. Magnetic field is running this. Now, instead of a prop, I'm going to use my finger as an arrow mark, and I'm going to run in the direction of the magnetic field. Run in the direction. And now if I want to know the magnetic field at a specific point, I'll just stop over there. So for example, if I want to know what the magnetic field direction at the right side, it's going to stop. Notice it points down. If I want to know what the magnetic field at the bottom, it's going to stop. Hey, it's to the left. If I want to know what's the magnetic field to the left of it, upwards, and so on. So that's how, using the right hand clasp and then running your finger along that field line, you can figure out the direction of the magnetic field. So let's solve a couple of numerical. A wire.
I will be turning off the caption purposefully because I want you to read the statement and then see the video how he is solving, so that the concept will be more clear to you. Okay, see it very carefully. There is a wire that carries the electric current from west to east direction. So how is the flow of current west to east? I hope you know where is west and where is east. Find the direction of the magnetic field at a point directly below the wire. So we want to know what is the direction of the magnetic field below the wire. Okay.
Carries an electric current from west to east. Find the direction of the magnetic field at a point directly below the wire. Okay. So here we have to use east, west, north, south. So just to remember, this is north, this is south, right is east, left is west, up and down. So we have a wire that carries electric current that runs from west to east. So west to east is this way.
Yes.
So,
Is this west to east? Is this how your conductor should look like if the current is flowing from west to east? Yes. Okay.
from west to electric current is this way. We need to find the direction of the magnetic field at a point directly below the wire. So we have to find somewhere below it. So pause the video and see if you can try to do it yourself first. Alright, let's do this. So first step is to use your right hand and clasp this conductor this way. The thumb should point in the direction of the electric current, so it's going to be this way. And so the four fingers are telling me the magnetic field runs in this direction. I'm not going to use any props now. Let's just imagine this. And so the magnetic field runs like this way. So
Now what you can do is you can remove your four fingers, middle finger and all that with a single finger. Okay, because now we are not going to use bangles and all that stuff. So once you know how your fingers are curling, you can just remove it with a single forefinger.
I'm going to use my fingers to represent that.
See, this is how it is
And
flowing.
since I want to know the magnetic field below the wire, I'm going to stop below the wire now this way. And so below the wire, the magnetic field is to the north. This is not up, this is up, this is to the north. So the answer is to the north.
So is this clear? It is to be north. Any doubt? I will just play it again. Just see. This is how you will be clasping this particular conductor. Now once you clasp it, you know how your four fingers are curling up. So you can remove it and replace it with a single finger.
This direction. I'm not going to use any props now. Let's just imagine this. And so the magnetic field runs like this. And so I'm going to use my fingers to represent that. And since I want to know the magnetic field below the wire, I'm going to stop below the wire now this way. And so below the wire, the magnetic field is to the north.
So this is north, as you can see from this particular direction chart.
North. Not up,
South to north.
This is up. This is to the north. So the answer is to the north.
Is this clear? You can rewatch this video again and again. This is from Khan Academy, okay, and you can just try it out and let me know in case if you again face some issues, right? Is this clear? How do we perform it, and what is the application of right hand thumb rule? Okay, you can again rewatch that video. It is very beautifully explained. The channel name is Khan Academy. So there are n number of numericals also. Just try it out and you will get to know. Okay. Next is magnetic field due to a current through a circular loop. Now in this case, your conductor is in the form of, yes, what is your conductor in the form of? It is in the form of a circular loop, as you can see over here, figure 13.8. Right now we have just seen about a straight conductor. Okay. Yes, we have seen a straight conductor and we have seen it forms a concentric circle. It was concentric circle because you have seen You have seen how your fingers were curling up. It was going in the round and round direction, right? So therefore it was a concentric circle. Same thing happens in circular loop as well. You can see how the magnetic field lines are drawn. As we have discussed, the field lines never break at a point. This is how it will go. Okay, but just for convenience, they have just shown the halfway. Okay, so it keeps on going like this. Again the same thing, if you will increase the current, magnetic field will increase, so B is directly proportional to I. What happens if I increase the number of turns? In that case, what will happen? Any idea? There is only one turn right now. If I do 2 turn, 3 turn, 4 turn of this particular wire, what will be the effect on a magnetic field? Will it increase or decrease according to you? What should be the case? Yes. If there are n number of turns, in that case, yes, it will increase. But why? What is the reason? Yes, what is the reason? Earlier there was one turn. Now suppose there are two turns. So obviously in two turn, the magnetic field will be more. Yes, because it is directly proportional. Why it is directly proportional? Because see, in a single turn there will be some current flowing and there will be some magnetic field that will be generated. If you have two turns, will the amount of current increase in that case? Yes or no? If it is a two turn, the current will increase, right? So current will now be increased comparatively to the first case, and so is the magnetic field. If you have three turn, again you could keep on adding the current. It is going to be increasing once you start just adding n number of coils. So you can say that B is also directly proportional to n, where n stands for number of coils. Okay, this is because the current in each circular turn has the same direction and the field due to each turn then just adds up. So this is a relation that you can find it out from this. Okay, this is the only content that is important from this particular section. We will just see the video of a solenoid. Yes, this we have already seen how the pattern looks like. Then we have seen how is the pattern in case of straight conductor. It is in the form of concentric circle, because when you hold the wire using your right hand, the way of fingers curl, that gives you the direction of magnetic field. Okay, just go through the in-text question. They are easy ones and we have covered in the content part.
And mark the boundary of the magnet.
This is same. We have covered this. See,
the south pole of the magnet. Join the points marked on the paper by a small.
Okay, this we have done it in the first lecture, how it is flowing. Yes, what is a solenoid? So a solenoid is just a coil of wire. This is a coil of wire of n number of turns. Why is it such a big thing to study about then? A solenoid is just a coil of wire, but when you run a current through it, you create an electromagnet. Electricity, with the help of electricity, you are creating a magnet, therefore electromagnet. Electromagnets are particularly useful because unlike regular magnets, they can be switched on and off because you are directly supplying the electricity, right? So you can just turn it on, turn it off, and strengthened by increasing the current flowing through them. It doesn't happen in regular magnets. Regular magnets have fixed field strength. But in case of electromagnet, you can increase and decrease the field strength. How will you do that? Increase the current. If you increase the current, the field strength will increase. If you decrease the current, the field strength will decrease. Yes. So that is how they are very, very different from regular magnets. In regular magnets, your poles are fixed, North pole and south pole. But in electromagnet, you can just reverse the poles. How can you reverse the pole? You can reverse the pole by reversing the direction. So you know that when a charge moves, it produces, then it is okay, rotation is there. In that case, it is electric motor. It produces a magnetic field. Physicists have figured out that it's because both the fields are part of the same force nature, that is electromagnetism. Okay. Because of this, we can create a magnet by simply running a current through the wire. So just see this video.
Take a long coil with many circular turns of insulated copper, wrapped closely in the shape of a cylinder. This type of coil is called as a solenoid. The electromagnetic effect of a solenoid is used in several appliances. Let us pass electric current through the solenoid and observe the pattern of magnetic field lines demonstrated here. The magnetic field lines in a solenoid are same as in a bar magnet. They pass through the solenoid and return from the other end. The field lines inside the solenoid are parallel to each other. The parallel lines will have the same magnitude of the magnetic field. That is why the solenoid has a uniform magnetic field. If we suspend this current-carrying solenoid freely, it rests pointing north and south, just like the suspended magnetic bar does.
We will see more about solenoid in the next class. I just wanted to give you a brief picture of what it is and how it is generated. We will see it in more detail in tomorrow's class. Okay, so we are done with the class. Thank you, everyone.
If you like our videos, do share them and subscribe to our channel. If you want awesome quizzes, write to us. Keep watching and keep learning with Walnut.